In this presentation, we will be looking at how to identify offensive language in social media posts. We will summarize our solution using the phases in the cross-industry standard process for data mining methodology. The business objective is to develop classifiers for identifying offensive language in social media. The primary goal of this project is to build appropriate classifiers which can be applied to unclassified data, in this case social media posts, and decide whether the post can be considered offensive or not. The data mining objective is to turn the training dataset and the test set into Vecca-compatible format and then explore different classifiers and evaluate the result. Our success criteria is to find a classifier with a relatively high precision, while especially focusing on the number of offensive comments classified as not offensive.
The data that we use was provided in TSV and CSV format. This includes the training set, the test set, and the correct values for the classification of the test set. After looking at the files, we decided that the tweets, their IDs, and the values for subtask K would be appropriate attributes, and that subtask K would be the specified class. The files also include some other information for subtasks B and C, but it is not relevant to our problem, so we didn't use it. At a glance, we notice that most of the tweets are not offensive, so they would form our baseline. There are also many curse words and profanities that can be used to identify offensive language. We should note that deciding whether a tweet is offensive or not is more or less subjective. However, most of the values that were given are sensible, so we use the data without changing the classification.
When preparing our data, we had to think about what things make a tweet offensive or not, such as emojis or hashtags. Some words are too common to provide any real meaning to a tweet. It is very hard for Twitter to tell what is offensive and what is not, such as the hashtag learn a code fiasco in February. We need to change our data from a .tsv file to a .arff file so that Weka could read it. Some problems were that there were 2 extra columns that we did not need, there was no metadata, and there were lots of quotations and commas which would interfere with Weka's parsing. The first thing that we did is split up all our data and remove these commas and quotation marks that could cause errors. The next thing that we did is find a dictionary full of common words. For each of our tweets, we could remove words that we thought were too common. This value could be changed and we can see how it would affect our results. Finally, we wrote the metadata down at the top of the file and then went through our lists to write all the new data down, putting all our tweets inside quotation marks. Once we had this finished, we could upload this file to Weka and we could use it to parse and analyse all our data.
Further filters need to be applied to our data before analysis. Weka supplies a string-to-word vector filter which runs through the data and assigns each unique word a value for the number of times it appears in the dataset. Weka supplies classifiers, which are the machine learning algorithms for data mining tasks. Several different classifiers were tested on our data with varying success rates. The first classifier used is 0R. This is Weka's baseline algorithm and the results are used to compare the outcomes of the other algorithms. The J48 classifier takes the supplied data and generates a decision tree. The method is better suited to numerical data but can be used for text data also. The naive Bayes method applies the Bayes theorem to the data to determine the probability of the classification. The random forest classifier is similar to the J48 method, but it produces multiple trees that use a different subset of the training data. The last method used is the logistic classifier. It is another probability classifier that takes the number of instances of each word into consideration to produce the probability of the outcome. Different parameters were applied to the data to get more accurate results. The minimum term frequency filters the words that appear more than a chosen amount, and normalizing the data also helps by reducing redundant and repeated data. The data is modeled after each classifier run. The percentages of correctly and incorrectly classified instances is shown, along with a confusion matrix showing exactly how many instances were classified in each way.
Each classifier will be evaluated against these goals, with the main goal being to maximize correctly classified offensive posts. Here are the results produced from all the classifiers run on the same training and test data. The key values to take note of here are the high accuracies of the random forest and logistic classifiers. Logistic has the highest accuracy at 79%, closely followed by random forest at 78%. Additionally, the logistic classifier also had the lowest false positive rate at 18.2%, with J48 having a similar rate of 19.7%. The overall best classifiers were logistic and J48. If we were to deploy a model, it would be the one produced by the logistic classifier. This is because logistic has a faster build time, greater accuracy, and a slightly lower false positive rate. Although J48 classified more offensive posts correctly, this was only by one post, and we also want to minimize non-offensive posts being classified as offensive. We should also take into account how using a string-to-word vector filter does not precisely convey the meaning and context of a particular word. This means it will be extremely difficult to get a higher accuracy than that of a logistic classifier. Thank you for listening to Team Flush Mining.